Hi, I'm Norman Wahlberger, and today we're going to have a good look at the spread law, which is the third of our four important laws for trigonometry in the hyperbolic setting. The spread law in the hyperbolic setting has exactly the same form as the spread law in rational trigonometry. And I probably should say that all four of our main theorems, Pythagoras' theorem, the triple quad formula, the spread law, and the cross law, in hyperbolic geometry are more complicated to prove than they are in the Euclidean affine setting. In fact, a computer is a very important tool to discover the proofs of these theorems. And the proof that I'm going to give you of the spread law here today also was discovered by using a computer. Although in principle it's possible to check the proof directly with pen and paper. So we're concerned with two lines, capital L1 and capital L2, and here are our conventions. Proportion L1 to M1 to N1 in round brackets is L1. Their proportion L2 to M2 to N2 in round brackets, that's L2. And the definition of the spread between the two lines, it's capital S of L1, L2. It's 1 minus L1, L2 plus M1, N2 minus N1, N2 all squared divided by L1 squared plus M1 squared minus N1 squared times L2 squared plus M2 squared minus N2 squared. And I hope this kind of expression is starting to look very familiar. This is exactly the same form as the form for the quadrants between 2 points. And here's an important alternate way of writing it. We can get everything over a common denominator by replacing the 1 with this thing over itself. And then the numerator can be rewritten as this thing squared plus this thing squared minus this thing squared. And I just make this obvious observation, the quadrant spread duality, that if you have 2 points, A1 and A2, the quadrants between them is the same as the spread between the dual lines. Because to go from points to the dual lines, it's just a question of replacing the square brackets with round brackets. And since the formula for the spread is exactly the same as the formula for the quadrants, this is obvious, but it's important to say it. So now let's have a look at an example of spreads which show you that this really is, in some sense, pretty close to the Euclidean definition. So let's have a look at the example where the two lines both have third coordinate equal to 0. In that case, if you look at the second form for the spread, then of those 3 terms that appear in the numerator, 2 of them are automatically 0 because of these zeros in the n position. So it means that the spread between these two lines is, well, there's only 1 term left in the numerator. The 2 minus signs have cancelled, and we get L1 M2 minus L2 M1 all squared divided by L1 squared plus M1 squared, L2 squared plus M2 squared. This has exactly the same form as the Euclidean spread. So it means that if we're looking at 2 lines which go through the origin, because the point that they both go through is the origin 0, 0, 1, say L1 and L2, then the hyperbolic spread, the capital S, is the same as the Euclidean spread, which we usually denote by little s. So at least for this particular point, for the center of our null circle, the two notions, the Euclidean notion of spread, the hyperbolic notion of spread, they do agree. That's not true if we move our point elsewhere, but at least it does show you that in that particular case, the two notions of spread are the same. So here's our spread law, the hyperbolic version. Suppose that A1, A2, and A3 are distinct points, with Q1 being the quadrants between A2 and A3, Q2 being the quadrants between A1 and A3, and Q3 being the quadrants between A1 and A2. And with S1 being the spread between the lines A1, A2 and A1, A3. S2 being the spread between the lines A2, A1 and A2, A3. And S3 being the spread between the lines A3, A1 and A3, A2. Then S1 over Q1 equals S2 over Q2 equals S3 over Q3. And here's our notation for that. We have 3 points, A1, A2, A3. I've put them outside our null circle for once, but they can be anywhere they want. Then the quadrances are Q1 right there between A2 and A3, Q2 between A1 and A3, and Q3 between A1 and A2. And the spreads, S1 is the spread between this line and this line. S2 is the spread between this line and this line. And S3 there, the spread between this line and this line. And those 6 numbers are related by this law. Okay, so we are going to prove this. And we're going to at least proceed in a naive way. We're going to start by first assigning values to the points A1, A2, A3, so we have something to work with. So we'll suppose that A1 is the proportion x1 to y1 to z1, A2 is the proportion x2 to y2 to z2, and A3 is the proportion x3 to y3 to z3. So our strategy is to calculate things in terms of these 9 numbers. So we're supposing that these numbers are actually known to us. Okay? And we're going to try to find, first of all, S1, let's say, in terms of these numbers. So S1 is the spread between the 2 lines, A1, A2, and A1, A3. That's 2 of the lines of the triangle, and let's call those lines L2 and L3. Actually, probably this line here, the line joining A1, A3, that should be L2 right there, and the line A1, A2, we'll call that L3. That's more consistent notation. So those lines have some coordinates. So say L3 is L3 to M3 to N3, and L2 is L2 to M2 to N2. And the join of points theorem allows us to write down what these proportions are in terms of the coordinates for A1, A2, and A3. So there's 2 expressions here. Say this one here, L2 is y3 z1 minus y1 z3. M2 is z3 x1 minus z1 x3, and N2 is x1 y3 minus x3 y1. And the same for L3, M3, and N3, the 3 coordinates here, formed by joining A1 and A2, the coordinates involving the coordinates for A1 and A2. So explicitly, what can we say about the spread S1? Well, it's, remember, 1 minus L2, L3 plus M2, M3 minus N2, N3 all squared, divided by L2 squared plus M2 squared minus N2 squared, times L3 squared plus M3 squared minus N3 squared. So I've written that right down here. That's the definition, essentially, of the spread between these 2 lines. And I've got everything over a common denominator. Okay, now we have our work cut out for us. Because we have to replace these L's, M's, and N's with these expressions here to get something involving the X's, the Y's, and the Z's. Because those are the original coordinates for the points A1, A2, and A3. And you can see it's going to be somewhat involved. The numerator, which is the especially interesting part, this L2 squared, you're going to have to put this expression here inside there and square it. M2 squared, you're going to have to add the square of that. Then you have to subtract the square of that. This term, the square of this, plus the square of this, minus the square of this. So we have to multiply those 2 things. And over here, this times this, plus this times this, minus this times this, all of that, all squared. So it's going to be a very long expression. By the time we expand it all out in terms of these numbers x1, y1, z1, x2, y2, z2, and x3, y3, z3, it's going to be a big expression. And now a miracle occurs, as it does for pretty well all of these laws. The miracle is that that long expression actually has a beautiful, simple, relatively simple, factored form. Here it is right here. So that numerator there ends up being exactly minus x1 squared plus y1 squared minus z1 squared times this whole thing here squared. And what is this whole thing? It's an expression that we've seen before. It's exactly the determinant of the 3 by 3 matrix that you get by putting x1, y1, z1 in the first row, x2, y2, z2 in the second row, and x3, y3, z3 in the third row. So it is x1, y2, z3 minus x1, y3, z2 plus x2, y3, z1 minus x3, y2, z1 plus x3, y1, z2 minus x2, y1, z3. And it's all that determinant squared. It's a remarkable polynomial identity. The denominators involving the L's, M's, and N's, okay, we could also replace those with these expressions, but it's not that important for us to do so. We're going to leave them here with the L's, M's, and N's. It's this numerator that's really the important thing for us. And while we have this determinant in front of us, let's make an observation about how to remember these factors. So the first one, x1, y2, z3. How do you go from this one to the next one? You get it by interchanging the indices 2 and 3. So the 2 becomes a 3, the 3 becomes a 2. Now to go from this one to the next one, we interchange the indices 1 and 2. So the 1 and 2 become 2 and 1. And then at the next step, we interchange 2 and 3 again. So we're either interchanging 1 and 2 or 2 and 3. And we alternate. First 2 and 3, then 1 and 2. 2 and 3, I guess it's over here. 2 and 3, then 1 and 2, 2 and 3, 1 and 2, 2 and 3, and 1 and 2. So here we interchange 2 and 3, here we interchange 1 and 2, 2 and 3, 1 and 2, 2 and 3. And if you did it once more, you interchanged 1 and 2 here, you would get back to there. So it's actually not that bad to try to remember that formula for the determinant. Okay, so here is the heart of the proof. The heart of the proof is that this thing times this thing minus this thing squared, when you plug in all those things, factors in this beautiful way. Let's call this formula star. We're going to use that to prove the spread law. So the spread law involves the ratio S1 to Q1. So let's write down what Q1 is in terms of X, Y's, and Z's. For that, it's useful to also introduce L1, M1, and N1, which are exactly the same, parallel to L2, M2, and N2, and L3, M3, and N3. So there's the expressions for those. And those are the coordinates of the line L1 joining A2 and A3. Okay, so what is Q1? Well, for the formula for the quadrants between 2 points, this is the quadrants between A2 and A3. And here's the formula for it. It's exactly the same kind of thing. X2 squared plus Y2 squared minus Z2 squared, X3 squared plus Y3 squared minus Z3 squared. And here's that sort of alternate form for the quadrants between 2 points involving these 3 numbers squared. And there's a minus sign in front of it. That's a formula for the quadrants between A2 and A3. We're going to call that double star. So now let's combine the star and the previous page and this double star formula. We're interested in S1 divided by Q1. All right, if we divide by Q1, it means we're inverting this. So the X2 squared term that's right there, the X3 squared term appearing right there, and this L1 squared term appearing in the denominator right there. The Q1 term then is responsible for this factor, and this factor. And there's also a minus sign. So the S1 term on the previous page, the starred formula, involved also a minus sign together with this term and the d squared term, where d was this long expression, divided by L2 squared and so on times L3 squared and so on. So this is a direct combination of the star and the double star formulas. The double star formula contributing this term, and this term at a minus sign. The star formula contributing this term, this term, this term, and this term, and another minus sign. The two minus signs cancel, and so we get S1 over Q1 is this. And now we observe that this quantity is symmetric in the three indices. Why? Well, because here, here, and here, these three terms are obviously symmetric if we interchange indices. These three terms are obviously symmetric if we interchange indices. And what about d squared? Well, that's the square of the determinant of the matrix that you get by putting the rows A1, A2, and A3 in. Now, if you interchange any two rows in a determinant, the determinant changes by -1. And its square does then not change. So the determinant squared is unchanged by permutation of the rows. In other words, it's independent of when you switch the indices. So that means that this expression is going to be the same thing that you get when you calculate S2 over Q2 or S3 over Q3. It's symmetrical in the three indices, so these three ratios have to be equal. And that's a proof of the spread law. Admittedly, a bit of a tour de force of polynomial algebra. High school algebra, nothing fancy, nothing too sophisticated, but the size of things is reasonably impressive. So that work that we've done in putting together the proof for the spread law has some other additional consequences that I now want to harvest for use later on. So while we still have those formulas fresh in our mind, let's have a look at some interesting consequences. First of all, the formula for Q1. Let me remind you what that was. It was this term here divided by this term times this term. Well, of course, there's a corresponding formula for Q2 and a formula for Q3. And if we multiply all of those three together, then we're going to get this term times this term times this term in the numerator. And, well, we're going to get the x2 squared, x3 squared from Q1. From Q2, we're going to get x1 squared times x3 squared. And from Q3, we're going to get x1 squared times x2 squared. So when we multiply these three together, we're getting the product of each of these twice. So each of them squared. Each one of these individually has a minus sign, so three minus signs multiplied together gives us still another minus sign. Now let's have a look at what we get when we multiply this formula by that triple star formula that was the consequence of that big formula that we wrote on the previous page. The formula for S1 over Q1. Okay, the S1 over Q1. What did it have? Well, it had a d squared term in it. It had this times this times this in the denominator. So when we multiply by Q1, Q2, Q3, that's going to disappear. And it had x1 squared, x2 squared, x3 squared in the numerator. So again, when we multiply by this, those numerators are going to be disappearing, but because these have factors too, they're going to be appearing in the denominator. And of course, if we multiply S1 divided by Q1, Q2, Q3, then we get Q2, Q3 times S1. There's still a minus sign. Now, by symmetry, because S1 over Q1 is the same as S2 over Q2, this is exactly the same thing that we're going to get if we multiply S2 over Q2 by Q1, Q2, Q3. In other words, Q1, Q3, S2. And that's the same thing as we get when we multiply S3 over Q3 by Q1, Q2, Q3, namely Q1, Q2, S3. So these three products of two quadrances and one spread, they're all equal. And furthermore, what they're equal to, this expression here, is quite an interesting and important invariant of the 3 points that we started with. We're going to give it a name. We're going to call it the quadri of the triangle, and we're going to denote it by an A, sort of a calligraphic A. So A of the triangle A1, A2, A3 is this expression. It's a very interesting expression. So this determinant squared in the numerator, and here we have the products of these quadratic forms. And there's also a minus sign. And this thing is well defined because if you multiply, say, the coordinates of A1 by lambda, then this ends up being multiplied by lambda squared, and this expression inside gets multiplied by lambda because each of these terms has exactly one of these three terms in it, and when we square it, we get a lambda squared coming out. So this expression is invariant under scaling of any one of the coordinates A1, A2, and A3. So it really is a well-defined expression. We will see later on that this is the most important single invariant for the triangle itself. In some sense, this is somehow some kind of hyperbolic analog of the square of the area, very loosely. But we're going to talk more about the quadri, and it's going to end up playing an important role in the later development of this subject. But it's a nice place to introduce it now because it's kind of a consequence of these formulas that we obtained in the proof of this spread law. So we'll see more about the quadri and its significance later on. Let's now have a look at some exercises to get you making some computations with the spread law. Okay, so these three exercises are a little bit the same. I want you to compute quadrances and spreads for various triangles and verify the spread law and find the quadria. So for example, for the 3 points A1, A2, and A3 here, involving some variable parameters x and y, calculate the quadrances and spreads in terms of x and y, verify the spread law. In other words, check that S1 over Q1 really equals S2 over Q2 really equals S3 over Q3, and find the quadria of the triangle. Same kind of thing for this triangle, 1, 1, 1, x, y1, x minus y1. And same for this triangle, which not only has some x's and y's in it, but also a z. Practice doing some algebra, computing quadrances algebraically, and getting some confidence that these laws really do work. All right, so we've got 3 out of 4 so far. The last one that remains is the cross law. So that's what's on the agenda for next time. We're going to look at the cross law and we're going to prove it. And then we will have established the 4 main trigonometric laws for hyperbolic geometry. These are the most important theorems in the subject. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.